about a meteorite, and that is the rock that actually hits Earth that we can pick up and we can study. So I have a few examples of meteorites that I want to pass around as well. Largely, you can decompose meteorites into three different categories. You've got iron-based meteorites, and you've got rock-based meteorites that look very much like terrestrial rocks. And then you've got this third type that's sort of a mix between iron and rock, like in equal portions. So first, I want to show you all an iron meteorite. So, did you know that iron in its native form as a metal is extremely rare on the planet? There is only one known deposit for natural iron on Earth, and that's in Greenland. Usually when you find iron, it's in an ore state, so you only have small flecks of iron throughout the rock. So, this is an interesting tidbit. Humans, when we started using tools, right, iron-based tools, the iron that early humans used before 6500 BC was found in meteorites. That's how they used their tools. So that was because it took them, another few millennia to discover melting out the iron flecks from ore to create their tools. So I thought that's really fascinating, right? So here's an iron meteorite. When you touch it, you're going to feel how enormously dense this thing is. For its size, it is extremely heavy. That's one thing you're going to see about this. You can also see on it, there's going to be these like little thumbprints, it looks like, and that's formed as this rock comes hurtling into Earth's atmosphere and heats up. It gets ablated, so that's kind of cool. You can put your fingers in there and touch that. And so I'll start passing this around now. You can also start to see that the iron's being oxidized on the surface there. So that's another reason we don't find iron in great quantities on the surface of the planet, because it's chemically reactive and it'll start to break down. So where does this rock come from? So the idea here is that this iron, iron meteorites that are predominantly composed of iron, have formed from the interior cores of protoplanets in the early solar system disk. So this, would have probably been the interior core of a planet that's failed, that has collided, broke apart, and now has collided with Earth. What else to say about iron meteorites? They're pretty, so these are actually quite rare when it comes to meteorites. They're about 20% of rocks that fall from space are iron like this, which is interesting considering that these are very popular in meteorite collections. Why would that be the case? Yes?
Maybe because it's rare?
Yeah, why? Because it's rare, yet so many people that collect meteorites have one of these.
Supply and demand.
Supply and demand, what do you mean?
Lower the supply, the more the desire for it.
True, but why, if it's so rare on Earth, like why, I'm trying to say, why is it so easy to come by?
Easy?
Maybe, in one regard. Okay, I'll give you a hint. It's iron. We can detect it with metal detectors. They're really easy to find if you go to an impact crater, you just search around with some equipment. It's one reason. They also look really different than rocks here on Earth. You'll see it has a very different structure, and it's very heavy. So it immediately stands out to somebody who's hunting for these things. Whereas the next one I'm going to show you looks very, so you could be fooled into thinking it's a terrestrial rock. Okay, so this brings us to the second type of meteorite, which is a rock type. So this is the most common to fall to Earth, a rock type of meteorite. However, it is very special, and I'm going to tell you why. When you look at this, you're going to see small round features in it, small inclusions. Okay, these are called chondrules. Pass this around. And okay, let me just paint you a picture of how that thing formed. So it's special because it is the rock in the solar system. This thing has formed likely in the earliest stages when our star was collapsing out of the pre-solar nebula and had this accretion disk around it. There was dust and gas in this accretion disk. The dust started to collide and stick together, forming like rocks like this, right? But in the surrounding vicinity, there was also a mineral called like a silicate mineral that got heated all of a sudden and melted and turned spherical because it melted, right? That was accreted onto this growing dust rock. And that's what you're seeing inside of this meteorite, these little inclusions. They're round little specks, and these are these accreted, like spherical melted things that happened in the disk. Why is that interesting? Because that has stayed the same throughout the entire history of the sun and the planets. That is pristine material that has never melted or chemically interacted with other things in that meteorite. It stayed perfectly spherical from the time that it formed in that meteorite, which dates that thing to 4.5 billion years old. The material that's made up of this rock is the founding, like the precursor to all planets in our solar system was made out of that material. So understanding how chondrules form and were, accreted onto these early rocks is a key open question in understanding how planets even form in the first place. And the last kicker about this special meteorite that you guys are going to see is that contained within it are over 600 organic compounds, including hydrocarbons, amino acids, and a whole range of other organic